In this session, we look into how to formulate a linear programming model. The learning objective of this course actually is to help you to use a mathematical programming method to solve or to make decisions in the sophisticated real-world situations, for example, supply chain related decision making process. So here you can see some examples of modeling problems. For example, you can make a production decisions, transportation decisions, inventory decisions, or manpower scheduling decisions. So many different kind of problems can be addressed by the mathematical programming method. When we look into how to solve a problem, normally we can go through different routes. So here in our course, we mainly using the quantitative method of the quantitative analysis. So after you can evaluate the solutions from your quantitative models or method, you can actually assist the decisions in the real world. A problem-solving process normally or often includes 6 steps listed here. You can start from a problem is detected, and then you look for a method to solve this problem. Then if you choose to do a quantitative analysis, then it requires we are able to model and calculate the solution, model the problem and calculate the solution. And then, of course, if the solution can be validated or verified, then you can use the solution to help make decisions in the real world. And then the business or the companies or the organizations may choose to implement your suggested solutions. If your solution is indeed better, you can help actually improve the real world businesses. So this slide shows the history of linear programming methods. We have these slides mainly because some in the previous lectures, some students are really confused about programming. They worry about this will be something about computer programming or coding. So here I just ensure you that here we do not emphasize anything about computer coding or programming. Here we only talk about optimization problems, including linear relationships. And then if we can use this method to solve some business decision-making problems, then for example, make plans. So then the plan sometimes is called programming. That's why this method is called linear programming. So it's a purely mathematical programming. It's not a computing method. So we use a small case to actually show how can we formulate a linear programming model. And there's a fixed 4 steps methods. So before we actually start to model this problem, we try to understand this specific case by define or identify all the parameters. So I just make this smaller. So hopefully you can still see the text in your own computer. Here I try to write down the formulation method or the steps. So first we start with the first step. So I write a step 1.1, identify parameters. So if I write everything down, will be a little bit slow. So be patient. So just let's read the text again. So first, let's see. This is a company production decision making problem or production planning problem. So we have the two types of products. So you have products, always it TVs. So we have one called Astor, one called Cosma. And then we can see in the first paragraph, this is a contribution margin, or sometimes we can see it's profit or price. So in contribution margin for Astor is 20 kroner each. Of course, it's a artificial example, cannot be so cheap. So Cosma is 10 kroner each unit. And then furthermore, we can see, so here is the contribution margin, and then we have a capacity limit for each product. So we have a production capacity, I just use a shorter name. Capacity is 70 and 50 units. So furthermore, we can see now the company or the factory also produces two items through two departments. So the production process, actually, we can use another table to put it down. So we have products A and C, and we have departments 1 and department 2. And this actually is two types of information. First is the production time consumption for each type of item. For Astor, it takes 1 hour in department 1 and 1 hour in the department 2. For Cosma, so in the department 2, 2 hours in department 1 is 1 hour. So you can see actually here 1 hour in department 2 and 1 hour in department 1. And then furthermore, we have the information for the production time limit for the two production units, department 1 and department 2. So we can name this as a production time limit. So in the department 1, the limit is 120 hours per day, and in department 2 is 90 hours per day. So you can also see these two numbers in the text. So this is actually all the data we have from the text. Now you can see the question actually is to formulate an linear programming model or LP model to maximize the total contribution margin given the capacity limits on the two TV taps and the capacities of department 1 and 2. So let's see, this decision or this plan is a daily plan. So we just need to make the decision based to maximize the daily contribution margin. So this is the first step. We identify all the parameters and we identify the question. So now we can actually come to next step. We can name it as step 1.2, or if you just see it's step 1. And then we define the decision variables. So I just use a shorter name, decision variables, define variables. So that's something we need to decide or to calculate. So here, the production plan for two types of products, so we can just define XA for the production quantity. We just define XA be the number of Astor produced per day. and XC, capital C, let's see, is a number of another product, Cosma. Is that called Cosma? Produced per day. So this is basically first step, identify parameters and define variables. So afterwards, we can actually construct the objective functions. So next step, step 2, we name it as a construct about objective functions, or we just write objective function. So the two things to think about. So if your problem is to maximize something or minimize something, so here in our question, we would like to maximize. So we write a maximize a contribution margin, CM. So it's a total contribution margin for two types of items. So your objective actually is the total production and total revenue or profit you can gain from this production. So we have a unit contribution for ester is 20 kroner, and then times your production quantity, so that's contribution margin from ester, plus you have a 10 contribution margin for Cosma times the production quantity for the Cosma. So that's how you actually decide your objective function. Then next step, so we can construct the constraints. So you can write construct constraints or just write constraints. So in this question, we know we have the production capacity. So I change the color of the pen. So this actually capacity, that's one constraint you can think about. And another constraint actually is production limit. So we try to formulate these constraints into mathematical relationships. So now let's say the capacity for ester, so production capacity for ester, so which is 70 units. So I just write here, so you produce XA should not be greater than 70 units. So similar for Cosma, it should be less than or equals to 50 units. So this actually is constraint 1, constraint 2, and then we have constraint 3 from the production limits. So then we can see, again, I pointed here. So you know the total production time limit for department 1. And so this column, you have 1 hour for A, 1 hour for C. So your total production time consumption is XA. Sorry, I changed the color. So the third constraint will be XA plus 2 times XC. So should be less than or equals to the total production time available in department 1, which is 120. And the last constraint is so in the second column, so do not change color here, you can see I have a XA plus XC less than the total capacity, 90 hours. So these are the main constraints. So this is a production business case. So we should normally assume your decision should not be negative. So we see we have the decision variables equals to or greater than 0. We also call this as a non-negativity constraints. So from this case, you can see the linear programming formulation method mainly including 3 steps. So I use the 3 steps to describe the process in this course, but you can see this is 3 steps or 4 steps. So we start from identify parameters, then we define variables, then you construct your objective function, and then you construct your constraints. So that's necessary or main steps we normally go through. This is also the very important step for you to solve a linear programming model. If you do not have such a mathematical model, it's actually difficult later on when you try to solve the problem. Although it's possible, you can find a solution from the Excel solver without knowing a mathematical program. But that's compulsory for you to learn. You should be able to write down a mathematical model. Based on the previous description, now you can see we have standard formulations for a linear programming model. So you can see we have so decision variables, objective functions, and constraints. So then we're done for today's task. We know how to formulate a linear programming model. So we have actually formulated our case into a detailed linear programming model. So like here, so here, this model. But sometimes when your problem is large, so the model will also be very large. So then in that sense, we would suggest you actually to consider to use a compacted form of the linear programming model. So the compact form model, should make it a bit larger. Now you can see you put the decision variables or the coefficients of or the other coefficient of your model into matrix. So here we can see the objective function can be written as a vector product of c times x. So the c, small c, is the contribution margin coefficient of vector. Then the constraints can be written as a ax less than matrix B or vector B. So B normally is called the right hand side of your constraints. And then here we have A, normally is called a constraint coefficient. And of course we have X as a vector of your decision variables. Then you can write your mathematical model in a compact way. So look, the model is smaller. This normally works when you have 100,000 or many more decision variables or parameters. So this is not required, but it's good to know. So at least it should be able to write a detailed specific linear programming model. So here is a quick recap of the linear programming formulation. So the common features as we normally deal with a minimize or maximize problem, and there are some constraints or restrictions for your decisions, and there are alternative courses of actions. You can actually make different kind of decisions, and mathematical relations are all linear. So that's common features of the method or the problem. And then we also have the common components or the key components of linear programming model. Then here just corresponding to the 4 steps. So we have parameters, we have decision variables, we're supposed to find objective function, and then all the constraints. Here is a general form of linear programming formulation. So they describes all the different types of linear programming models. So of course, it's a most general form. You can see you have n decision variables, you have m constraints, and then the problem can be maximum or minimum, and then you have linear relationships. You can see the objective functions and all the constraints, they are all linear. They're actually, normally we assume it's non-negative constraints. So this is a very general form. Hopefully we can cover all the different types of problems you come across later. We have directly introduced you how to formulate a linear programming case, but we actually missed one important point in the mathematical methods. So we need to have a certain assumptions. So in the linear programming method, of course, we have assumptions. All the mathematical expressions are linear, and we deal with the certainty problems. So we call it deterministic problems. So all the parameters values are known with certainty, and the variability, decision variables do not need to take values in whole numbers. So now we do not consider integer decisions. Of course, you may ask, okay, the television production, how can it be divisible values? But for the time being, we only consider the continuous decision variables. And then we have a non-negativity decisions. It's easy to understand. And all the constraints must be the type greater than or equals, less than or equals, or sometimes it's not equals to. So we have, when you have these strict relationships, then you do not have a closed set, then we actually cannot find an optimal solution. So remember, we don't consider here. This is some extra hints about how to formulate a linear programming model. So again, that's a 3-step method we mentioned previously. So you first define decision variables and parameters. So here, different from what we have introduced is always remember, try to explain your idea verbally, so you actually interpret what you are doing here. You try to maximize or minimize the contribution margin, or this is a decision variable for production quantity, or and so on. And you may use the following questions to guide you. So what factors affect the objective function? What data do you need? And what do we have to make decisions about? What variables are necessary to formulate the constraints? And try to finish the sentence. The solution to our problem is to decide production quantity, production units for each type of product. So you invent a symbolic notation for the decision variables. For example, you can do the name-based. For example, we have XA, XC. Of course, you can write X extra, X cosma. So your option, your choice. Then second step, formulate an objective function. Again, try to do that verbally as well, because if you need to present your result to a business people, then they need to understand what you are doing. Decide if it is to be maximized or minimized, and then formulate constraints. Again, remember, verbally. And they also help you to check if you have considered all the constraints. We anyway meet in the Zoom, so we will try the extra exercise as a group discussion. And if you have any questions, you can also come. We discuss in the Zoom meeting.